Ignition sequence start. All engines are running.
We have taken tremendous steps.
We choose to go to the moon before this decade is out.
We have achieved the earth-shaking, the breathtaking, the groundbreaking,
One small step for man,
and left a mark in the heavens. Our successes build one upon another and amplify what is possible.
The dawn of Orion.
It's time we take the next great leap. We're building the next chapter of American exploration, returning to the moon to stay, so we can go beyond to Mars, to expand what's possible and further our understanding. The architecture for these missions is already taking shape. We will go with new systems, bold designs, and a sustainable mission. You can hear it, taste it, touch it. We are going. We are training, testing, pressing our pioneering spirit into every component, defining our resolve with every line of code, and securing our success with every welcomed partnership. This is not hypothetical. This is not about flags and footprints. This is about sustainable science and feeding forward the advance of the human spirit. Because we are the pioneers, the star sailors, the thinkers, the visionaries, the doers. And because we stand on the shoulders of giants to go farther than humanity has ever been, we will add our names to the rolls of the greatest adventurers in history. Every day, every mission, we advance this calling. We are NASA. And after 60 years, we're just getting started.
Well, that was pretty exciting. As you know, I think from day one at NASA, it's always been an exciting journey. Welcome to another episode of the San Diego Air and Space Museum's Aviation and Space video series. I'm Jim Kidrick, President and CEO of the Air and Space Museum here in San Diego. Today we have a very, very special guest from NASA, Mr. Johnny Heflin. Welcome, Johnny.
Oh, thank you. Thank you so much. I'm honored to be here.
Well, so are we, and we appreciate you joining us. And the NASA Air and Space Museum here in San Diego partnership is very strong, and as I said, very appreciated. We've also got Samantha with us. Samantha is, we're calling her our young student reporter, and she's also going to participate when we get to the Q&A after Johnny's presentation, and she always provides to us a very interesting perspective that's so important, especially to NASA's future when they're looking at engaging young people like Samantha and others. So I'm going to read Johnny's bio just so I get it correct. So I might have my head down just for a second. And Johnny, if I screw this up at all, you may correct us when I finish. Okay, because it's a pretty impressive bio. Johnny Heflin is the manager of the liquid engines element of NASA Space Launch System, or the SLS, program at Marshall Space Flight Center in Huntsville, Alabama. He's responsible for all aspects of liquid engine implementation for the SLS, including design, development, test, and flight of both the RS-25 core stage and the RL-10 upper stage engines. Prior to his current position with NASA, Johnny served as deputy manager and contracting officers representative of the office from June 2014 until his current appointment in September of 2020. Previously, he was assistant manager of the SLS Program Integration Office from 2011 until he joined the liquid engines element. Mr. Heflin began his 30-year NASA career in the propulsion test laboratory. He joined the Space Shuttle Main Engine Project Office in 2000 as the manager of the Avionics Flight Systems branch. He was later named the Engine Hardware Design Manager, where he was responsible for the design, manufacturing, and flight safety of all Space Shuttle main engine hardware for the last 18 shuttle flights. That's a bunch of flights. Johnny received his Bachelor of Science in Electrical Engineering from the University of Alabama there in Huntsville, and he's been recognized for his contributions to NASA, including a Silver Snoopy, the Outstanding Leadership Medal, and an Exceptional Achievement Medal. Johnny, welcome. How many times do we say to our friends, it's not really rocket science, okay, but I probably can't say that to you today because I think it is kind of rocket science. And so we're actually going to kick it off with the first question. That'll get our conversation going. And feel free to make us smart, because we're not quite as smart as you. I was one of those who was a Navy fighter pilot for a bunch of years. I depended on those engines and avionics all working for me. And I was telling one of your NASA representatives, Patricia, earlier, we used to go by the procedure that if something wasn't working, the first step was on-off switch to off, on-off switch back to on, because we were limited in what we can do. So you worked on the engines for the space shuttle, and now you are helping develop the engines for the Space Launch System. How are the two projects alike?
The shuttle program was, well, first of all, thank you for your service as a Navy fighter pilot. That's wonderful. Thank you for that. The two programs are very much similar. Shuttle was an amazing program, historic, certainly accomplished amazing things, including building the International Space Station over its 135 successful flights. The architecture for the SLS vehicle is very similar to Shuttle in some respects. We are leveraging a lot of the propulsion elements that we flew for years as Shuttle, the solid rocket motors, as well as the RS-25, or what was formerly called the SSME, Space Shuttle Main Engine. Those have been ported over, if you will, for use on the SLS vehicle with modifications to support this particular vehicle architecture, which is significantly different than Shuttle. Obviously, it's more of a traditional vertical rocket versus Shuttle, which was more of a space plane.
I think that's a good call, space plane. I always said it was the greatest glider ever built.
Sure was.
And okay, so you've talked a little bit about how they're alike. How are they different?
The vehicle architecture certainly is different. That drives a lot of changes in environments that the components on the vehicle have to fly in. The flight dynamics are different. The fact that SLS is no longer reusable as Shuttle was. SLS is an expendable vehicle. That drives a significant amount of changes, and one of the fundamental differences in the two programs. Okay. What we found in Shuttle was reusability. Reusability is somewhat expensive to reuse. Getting to space is difficult. So to turn that hardware around and fly it again, and to put it back through all the paces to show that it's good for another flight, became somewhat expensive. Hence a shift toward reusability. I'm sorry, expendability in the SLS program.
Right. Well, because it seems like reusability is one of the, I don't want to say new words, okay, but it's being used a little bit more by some of the programs. If we look at the Musk programs and Blue Origin, with Jeff Bezos, they both believe in reusability as much as they can, as you do, realizing you can't reuse everything, you can't make everything brand new, for the next mission. So how much more powerful are the engines in the Space Launch System than the rockets for the Space Shuttle?
So the engine is fundamentally the same. The difference between the former SSME and the current, what we've currently labeled the RS-25, really is we've modernized the avionics to overcome obsolescence, and we're flying it at different conditions. The Space Shuttle main engine was operated at 104.5% in power level in flight, where for SLS, those engines have been uprated to fly at 109% power. And the operating conditions are different. The inlet pressures, because the vehicle is now tall, so the weight of the propellant from that additional height raises the inlet pressure on the engine. So that required quite a bit of certification to that new environment.
Well, I think you brought up a great point. When you say 104, 109%, most people would say, what do you mean over 100%? It's that classic, how do you go over 100% and effectively do that for some window of time? Is it time limited?
No, it goes back to the heritage of Shuttle. When the SSME was initially designed, it had a target power level.
Okay.
That they dubbed 100%. And over the years, as we evolved that engine, they were able to increase the pressure. So they're running up at a little bit higher power level than we were before. So rather than rebaselining, they kept the same terminology and it became 104.5%.
Okay.
But basically, it means we're pushing the engines a little bit harder. But due to other changes in the engine system, the environments that the engines see is well within family of what we've seen before. So it's really a balance, right? So it's running at a higher power level, but pressures and temperatures in the engine, because of other changes, are well within experience what we've done before.
Okay.
So we've evolved the engine, upgraded avionics, certified to the new SLS vehicle architecture without sacrificing performance or any of the reliability that we gained coming in from the Shuttle program in that 30 years of history with the engine.
I've always wanted to ask that question because one of the airplanes I flew, we intentionally over-temped the engine for the catapult shot, just to get an increase in the thrust, but it was a 2-minute limitation. And so this actually answers a question I've had for a long time. How's that?
Oh, that's great.
Yeah. Okay, so back when the Saturn V was created, back in the 60s to, send men to the moon, men and now it's going to be men and women, certainly, we were really breaking new ground. And we had to design and build something that was never built before. In short, we had to create new technologies from scratch. What kind of new technologies have we had to create for the Space Launch System? So, some of those improvements you were talking about that are new and exciting.
So let me think about the best way to answer this. With new technology comes cost and a certain amount of increased risk, right? Because you don't have the experience with that technology that you had before. So when SLS was stood up, it intentionally leveraged a lot of what we've used before on Shuttle to stay away from new technology development because it costs a lot of money to do that. Right. So the big new development on the SLS rocket is, of course, the Core Stage, which we'll talk about later when I get into my presentation. But let me talk specifically about the engine because we're doing some really exciting stuff there. And we'll talk about it a little bit more later. But when we restart production for future missions on the SLS program, we are really leveraging what's broadly called additive manufacturing to design and build parts. You guys probably know it as what's called 3D printing,
right,
of metallic parts on the engine. So that is super technology that allows us to, from a bed of metallic powder, using sophisticated lasers and technologies, basically grow those new parts out of that powder bed in orders of magnitude less time and cost for what we did and what you would have done doing traditional manufacturing. So that's a new technology that's really, really helping us bring down cost as well as build parts faster so that we can support production rates that we need to target. That new technology has required quite a bit of development work to show that it's good for human-rated spaceflight, but we are nearing the end of that activity. And the restart, what we call the restart RS-25s, or the next lots of engines that we build will leverage over, I think, 35 different pieces that are now built using what's commonly called 3D printing.
Well,
that's really exciting.
No, it sounds exciting. And you talked about your presentation. So let's get into that, and then we'll get back to some more Q&A after your presentation.
Sure. Okay. So, good morning, everybody. It is really my honor to be here. I'm going to talk to you about NASA's plans to return to the moon via what's called the Artemis Program. As you've heard, I primarily work on this space launch system, which is the rocket that's being built to support and enable the Artemis Program. So we'll get right into it. Let's go to the next chart. So what is the Artemis Program? The Artemis Program is NASA's new historic mission to send the first woman and the next man to the surface of the moon by 2024. We have named that program Artemis. Artemis in Greek mythology is the twin sister of Apollo and the goddess of the moon, so very appropriate there. As we talked about, the Artemis Program will put boots on the moon in 2024. Really exciting stuff. The video you're watching is, of course, the surface of the moon. The landing location that we've selected for those lunar landings is the South Pole. South Pole is a region that has never been touched before. No humans have ever been there. In the Saturn days, Apollo days, we landed around the equator. So we're going to the South Pole. It has a lot of things that enable our mission. You have very long durations of sunlight, which we utilize to leverage to generate power and support while we're on the surface of the moon. It also minimizes temperature excursions. It's much more stable because you're in the sun most of the time. That makes for a much more stable and suitable environment as we're there on the moon, surface of the moon. And is there water on the moon? We don't know yet. There's a lot of good data out there that we're excited to explore. So that's one of the goals of getting to that moon, where parts of it are in sun all the time. You're in real close proximity to surfaces of the moon that are in darkness most of the time. So where we think we may find water that we can utilize while we're there on the moon. Okay, let's go to the next chart. So the purpose of this chart really is to tell you that not all rockets, not all vehicle and mission architectures are the same. The mission, what it is you're trying to accomplish, really drives the design of the vehicle. So you can see on the graphic the difference in mission duration, temperatures, and orbital escape velocities that you have to hit to get there, right? So the SLS program is being designed to be able to support these. Shuttle, of course, was low Earth orbit, so it couldn't have gone to the moon, right? So you see a lot of that in the movies. You see, it's not like driving a car that you can take a launch vehicle and just decide to turn left instead of right and let's go to the moon instead of the space station, right? You can't. The vehicle must have the capabilities to do to support those missions, and the capabilities required are really driven by what those mission needs are. SLS, again, is being built to support this very purpose, which we'll get into the evolvable architecture of the vehicle on the next chart. So let's go ahead and go to the next chart. So now we're going to start talking about specifically SLS. What's the rocket do? The rocket is a flexible architecture that, as we mentioned earlier, is shuttle derived in terms of the propulsion elements that is designed to support this mission. It is what we call the Block 1 vehicle, which is the first rocket coming that is in design now. We're getting ready to test the first core stage down at Stennis. This rocket is the only exploration class rocket that's capable of sending humans to deep space and the moon, which is the purpose, right? The work of going to the moon is also a proving ground for later missions to Mars. So the SLS rocket is being built with the capability to support all those missions. The rocket is it's big. It is a very big rocket. It stands over 320 feet tall. Let me read these so I get these statistics right. 5.7 million pounds is what it weighs. 8.8 million pounds of thrust. So that what that translates to is a capability. What can the rocket put, what can it lift, what can it get to the moon, right? So that's the whole point. So we can put, this rocket will be able to put 57,000 pounds to what's called translunar injection. So 57,000 pounds that we can put to the moon. That's a lot, right? That's a lot of weight. Let's see. Let's go ahead and go to the next chart. Get into more of the specifics. We'll talk about how big the rocket is. So you see the graphic. Statue of Liberty used as the reference point. You can see that SLS is quite a bit taller than the Statue of Liberty. It's a touch, I think, a touch shorter than Saturn V. Once you, when all the vehicle is stacked, you can see the graphics at the bottom, 364 feet tall, which is quite a bit bigger than the Statue of Liberty. So the block one, let me talk a little about this. The block one, the rocket in the middle, that's where we start. That's the first rocket. The first few rockets off the to the launch pad at Kennedy will be a block one vehicle. That utilizes 4 RS-25 engines at the bottom, 2 5-segment solid rocket booster strapped to the side, and a what we call an ICPS upper stage, which is a single engine RL-10 based upper stage. And that vehicle is designed to evolve to eventually get to a block 2, which is quite a bit taller. It has a 4-engine upper stage. The core stage and the boosters are the same. You add a more powerful upper stage to get you more lift capacity for future missions. That future evolvability up to 286,000 pounds lift capability. That equates just as a gee whiz fact to the weight of about 22 full-grown elephants. So that's a lot of weight, right? Okay, let's go to the next chart. So some of the components, the solid rocket boosters, these are leveraged off of Shuttle. They have been evolved. We've added an additional segment in the middle, so they now have 5 segments of propellant. So they're more, they're capable of burning longer, give you more power. So on the video, what you're starting to see, you're seeing castings that are being taken out of the pit at in Utah, where Northrop Grumman forms these segments as we pour the solid rocket propellant into those castings, where it's formed and then delivered to Kennedy Space Center for stacking into the larger solid rocket motor assembly. So what you're seeing now is a hot fire test of one of those boosters. That's what we call our qualification motor 2 test firing. So you can see how powerful the rocket is. It is, and I've been there and seen this test. It is extraordinarily impressive. A lot of power to support the SLS program. Okay, so let's talk a little bit about my favorite part. Of course, I'm the engines manager, so this is by default would be my favorite part, right? So the graphic you see top left, that's the core stage. That is the center part of the rocket, right? That's what holds the liquid oxygen, liquid hydrogen, cryogenic fuel tanks, propellant tanks that feed the 4 RS-25 engines that you see on the bottom. That picture of that graphic is being loaded onto the Pegasus barge at Michoud Assembly Facility, where that stage is manufactured, and it's being loaded on the barge in preparations to ship to Stennis Space Center, where it'll be tested. That core stage is in the test stand right now, getting ready for a green run. So on the bottom, you see a Airjet Rocketdyne technician. See, can we, yeah, there you go. He's one of our technicians down at Stennis Space Center, where we do all the engine assembly. The components are manufactured at an Airjet Rocketdyne manufacturing facility in California, and a litany of suppliers across the country All those parts are then shipped down to Stennis for assembly. You see one of our technicians there as he's working through checkout and assembly of the engines. And on the right, one of the prettiest things you'll ever see, that's an engine hot fire test. That is test stand A1 at Stennis Space Center. And you can't see the engine, it's buried in the structure, but you see the exhaust plume coming out of the bottom. The engine is vertically installed in the engine, so it fires down into that exhaust duct and mixes with water. And you create, it creates what we call rocket rain. We'll see a little bit more of that on the next chart. So let's go ahead and go to the next chart and watch the video. Okay, these are engines at Stennis being loaded in the storage containers and ready for shipment. You see a little of that stand there. The engine there is being loaded onto a lift to be installed in the facility down at Stennis Space Center. And there's the hot fire. The exhaust plume, of course, that as it moves up into the atmosphere, if you're standing in the wrong place, you'll get rained on. It is a clean exhaust, liquid oxygen and hydrogen mix and form water. So that's what generates what we call the rocket rain. If you're in the wrong location, you'll get rained on during the engine test. Okay, core stage. This is, of course, is the big new development that's part of SLS. We talked about engines, we talked about the booster. This is new. It's being built at Michoud Assembly Facility, which is just outside of New Orleans. It is being built by Boeing in cooperation with NASA. It consists of a very large liquid hydrogen tank, liquid oxygen tank, all the associated avionics and control systems that are required to operate the vehicle. So it's much more than just tanks. It is really, really the center, the core, and the brains for the SLS rocket. All new development, as I said, this core stage alone is 212 feet in height and 27.5 feet in diameter. When it's fully loaded with liquid oxygen and liquid hydrogen, it'll weigh over 2.3 million pounds. The hydrogen tank holds 537 gallons of liquid hydrogen, which is cryogenic. It's at minus 423 degrees Fahrenheit, so super cold, and a lot of it to be able to feed propellants into those 4 RS-25 engines and burn for over 500 seconds. So we'll consume that large amount of propellants as we burn that 500-second duration. Okay, let's go to the next chart. So this is test stand B2. This is also at Stennis Space Center, where the core stage is being ready to green run right now. It's installed in the stand. As you see here, that you can see the crane that was lifting. You have to go up over the superstructure and then lower that stage down into the test facility. It's a huge operation. The team at Stennis executed that beautifully. So here you see that as we're going through the steps to lift this massive core stage into the test stand. So what are we going to be doing? The purpose of the green run is really to exercise and validate all these new systems. So we have been for some time now in process of putting the vehicle or the stage through its paces, methodically working through all the various sets of checkouts and procedures in order to validate all the various avionics and power systems, the thrust vector control systems that will actually move the RS-25 engines that are on the bottom. So all that verification work and activation work has been going on for some time. And we are currently on track to load cryogenics into the vehicle or into the stage for the first time in October with a core stage green run hot fire, where we actually start all 4 of the RS-25 engines and run a full 500-second duration. That's what we call the actual green run. When everything's up and running You fire the engines, you consume all the propellants, and that hot fire green run test will be done before the end of the year. So it's a huge operation, very, very large, complex test program that the teams are just doing a great job pulling that off. Okay, so Artemis I. What is Artemis I? Artemis I will be it's a test flight. It's the uncrewed first flight of Artemis I, and the purpose is to fully integrate the launch vehicle, the SLS Core Stage, solid rocket motors, upper stage with the Orion capsule that is being managed out of Johnson Space Center in Houston, Texas. So we will fully integrate and we'll launch that vehicle, put it through its paces, and do a full integrated system verification in flight before putting people on the rocket for Artemis II. So let's go to the next chart. I think there's a video. So this is a Block 1 SLS vehicle, as we talked about earlier. It's highlighting the liquid oxygen and liquid hydrogen tanks. That is the nozzle of the RS-25 engines at the bottom. Main engine ignition and liftoff. So the engines start about 6 seconds before the boosters, the solid rocket boosters, in order to get the engines up to power level and verify operation. So we'll start the engines, run for about 6 seconds. The engine control system will go through its checks, make sure the engine is performing as expected. And then we light the solid rocket boosters and we are on our way. About 2 minutes into the flight, we jettison the solid rocket boosters. The RS-25 engines continue to fire. We jettison the launch abort system, no longer needed. 500 seconds later, the RS-25 engine shut down. The ICPS stage will separate. We will fire the RL-10 engine, which is part of that stage, and we are on our way to lunar orbit. That's going to be a fantastic day, certainly a historic day. So let's go to we'll talk a little bit about Artemis II. Artemis II is the first crewed flight. So after a successful Artemis I and we've verified all those systems in flight, Artemis II will load crew. The interesting thing, because of the way the lunar insertion orbit occurs, we will put people farther from the Earth's surface than ever before on Artemis II. So we'll be 23,000 miles from Earth and go farther out beyond the moon as we go through the lunar orbit than we've ever gone before. So this mission, it's a minimum of 8 days, could be as long as 21, depending on the objectives that the mission planners define that we want to execute. So that will be another historic day as we put crew back in orbit around the moon, as we do basically a flyby before coming back home. You see the Orion capsule with two of our astronauts inside doing checkouts and simulations at Kennedy Space Center. So that Orion capsule is at Kennedy right now. So it's being prepped for, it's being put through its checkouts in preparation for Artemis II. Okay, so Artemis III, this is the biggie. We put people back on the moon. This will be the next man and first woman on the surface of the moon in 2024. The purpose of that mission is to continue to verify, certify all the systems, the spacesuits, habitats, all the things that are necessary to define requirements for habitats and such as we move forward. All that'll happen on that first flight. 6.5 days is the current plan. 6.5 days on the surface before a safe return to Earth. So again, another just amazing historic day. Let's go ahead and go to the next chart. Just another graphic. So the Artemis missions that follow will continue to verify all the piece parts that are required in order to operate on the surface of the moon. They'll test the suits, the habitats, landers, all those integrated systems, as we also explore regions of the surface of the moon that we've never been to before. And all that really, the long-term vision is that's in preparation for trips to Mars. So we'll go ahead and go to the next chart. So the Gateway, what is it? Gateway is basically it's going to be an orbiting home base around the moon that the crew will use, a lunar laboratory, if you will, that the crew will utilize. They will fly to the Gateway and then go from there to the surface, establish a long-term presence in orbit around the moon in preparation for not just the lunar surface missions, but future missions to Mars. So what's that consist of? The first element is the propulsion and power element. That's really the core of the Gateway. That contract was awarded in 2019 to develop, launch, and demonstrate that power and propulsion element. The second element that will be brought up is what's called a HALO, Habitat and Logistics Outpost. Contracts also already been awarded to do that work as well. That's really the habitation outpost. That's what will provide the ability for humans to inhabit the Gateway. And that Gateway will be refurbished. Commercial capabilities. You'll provide cargo lift to the Gateway in the future. And there she is, the moon. Cannot wait. It's going to be historic, folks. This is exciting stuff. Sorry, give me 1 second. I'm trying to mute that.
While you're doing that, it's my understanding that Uber and Lyft are going to try for the replenishment contract.
I apologize. Okay, sorry about that. Technology is great when it works, right?
Well, you're the rocket scientist, right?
Yeah, I can't figure out how to turn off an incoming web call on a different platform.
Hey, while you're going through and continuing the presentation, your timeline for Artemis 1, 2, and 3, I may just have missed that, but I think to ensure that all of your fans, the NASA fans, the people keeping up with what's going on, what would you see those timelines as?
So it's all laid out to put boots on the moon in 2024. So that's what's driving the timeline.
Got it.
The Artemis 1 launch dates have moved around a little bit. You're developing new hardware, right? So that's always challenging. But it's all laid out in order to really drive toward that 2024 launch date to put boots on the moon on Artemis 3.
Well, that's great. It's pretty exciting. So end of the presentation?
I think we had another couple of charts that were really just kind of wrap up.
Okay.
I wanted to talk a little bit about what NASA really is. It's certainly a lot more than astronauts, right? It's, of course, engineers and scientists, but even well beyond that, NASA there is just an enormous breadth of skills and job opportunities within NASA. You see some of the pictures here. Interns in all sorts of different job opportunities, welding technicians, avionics, scientists, geologists. Just go ahead and go to the next chart. All sorts of things, business people who know how to manage contracts, and financial management people, and IT, intellectual technology, computer technology people. They're just an enormous number and breadth of job opportunities within NASA. So if you go ahead and go to the next chart, and you'll see kind of my get off the page chart, right? The best way to follow what's going on within NASA is social media. You see some of the links there on the page. You can also get to some of those jobs. I'm going to read these out to you. Some of the career opportunities. If you go to www.nasa.gov/careers, you can get a lot more information about job opportunities across the nation. Of course, we have NASA centers all across the country, and contractors that support us as well all across the country. So it's an amazing place to work. I've been here 30 years, all of it at Marshall Space Flight Center, and it's just been an absolute dream come true for me. So let me wrap it up. Core stage for Artemis 1 is being ready for hot fire test at Green Mine before the end of the year. It'll then be taken out of the stand and shipped to Kennedy Space Center, where the rest of the vehicle is currently there being prepped. So once the core stage is there, we'll stack that vehicle, get it checked out, and get it to the launch pad in preparation for Artemis 1. So we're well on our way. Lots and lots of hardware that's already been delivered to Kennedy, completed, and is there ready for vehicle stacking when the core stage gets there. So it's real. We're there. Tons of hardware, and even more in the pipeline for Artemis 2 and 3. That we're actually learning as we've gone through Artemis 1. First time we've done it on a lot of these parts, certainly in quite some time. We've learned just a tremendous amount of things that we're incorporating in the future hardware. So we're learning a lot of lessons that are going to allow us to build those future rockets much faster and more affordably going into the future. So with that, I think I will stop and open it up to questions if you guys want.
Well, we're going to bring Sam on, but
Okay.
I want you to know how well you've presented NASA's future and how exciting it's going to be for all those young people. One of our messages, certainly here at the San Diego Air and Space Museum, is it's a wow future. And right, and people like you and the rest of the NASA team are just making it more and more exciting, because this presentation for me kind of did put those dots all together. So I'm going to bring Sam on, and Samantha, and she's got a few questions for you, because it's her and her generation that are going to benefit from what you guys have been doing and maybe take it to that next level.
Absolutely.
Hello. Good
Hello.
morning. It's an honor to speak with you today. should we get started with the first question?
By all means, sure.
All right. How old were you when you realized you wanted to work on rockets?
So I'm an interesting person. I was not, I remember watching the lunar landing in '69. I was about 6 years old at the time. And I can remember I was lying in the floor with my television, my feet propped up on the television, which always irritated my mom. But so I remember watching that and being just completely mesmerized by what I saw, even at such a young age. So I have always valued and really been a huge fan of what NASA's done since its inception. Going to the moon, the things that we did, the things that were accomplished as part of Space Shuttle and Space Station. I don't know if you're aware, there's a website, and I can get it to you guys. I don't know off the top of my head, where you can actually track when the space station is going to come over in your part of the country, so you can go out and you can actually see it from the ground. It's really impressive. That was, of course, that being a part of being built via the space shuttle, and now moving on to SLS and going back to the moon. It's just an amazing thing that NASA's been able to do, and I've been a fan of it my entire life.
Wow, that's amazing. That's really cool.
The website is called spotthestation.nasa.gov.
Yes, very good. Very, very good. And it's fantastic. I still go out and watch it every chance I get. And it's very, very impressive to see.
I might follow you guys up on that. Okay. What would you tell someone my age who is interested in one day working for NASA?
Work hard in school. Of course, right? That's a given. That's anybody my age is always going to tell you that. What I would tell you is something my dad told me years ago, and I've heard it repeated. It's certainly not unique to him, that if you love what you do, you will never work a day in your life. And I love what I do. I get to work with some of the most brilliant people on the planet every single day. It has been life-changing. They're not just super genius, book smart people, which they certainly are, but they're also some of the finest human beings that you'll ever encounter. It's a fantastic place to work. What I would tell you is dream, right? Know what is it you want. You can dream, you can accomplish anything. If you work hard, you can be a part of this. I grew up not far from here in a small town called Decatur, which is about 20 minutes to the west. Real small town. My parents were both factory workers, and look what I've been able to accomplish. Look where I've been able to get to in my career. And I've been a part of I've really been a part of some of the most amazing things. I never dreamed as a child I would get to do the things that I have. So dream, and then go after those dreams. Certainly, it's all out there and it's within your reach.
That's very inspiring, especially for all the viewers out there. Okay. Where are rockets made, and how do you transport them from where they're made to where they launch?
So the rockets are made, you saw a little bit in the videos. The rocket is a collection of piece parts. The boosters are the solid rocket boosters are manufactured in Utah by Northrop Grumman, is the name of the company. They are then put on basically a train, and those segments are brought by way of rail to Kennedy Space Center, where they're then assembled into the larger solid rocket boosters. So those 10 segments that make up 2 solid rocket boosters are shipped by rail. The engines are manufactured primarily at the Aerojet Rocketdyne facility in DeSoto, California. Where they build components. They build a nozzle for the engine where the fire comes out, and all those various components, and those components are then sent down to Stennis Space Center, where they're assembled into an engine, a completed engine, that is then moved over to Michoud Assembly Facility in New Orleans, about an hour to the west, where they're integrated into the core stage. The core stage is built at Michoud Assembly Facility, again, just outside of New Orleans, where it's then barged to Kennedy Space Center. It's put back on the Pegasus barge. There's a good picture of it, where it is transported over the water to Kennedy Space Center. And Kennedy is where all those parts come together in the vertical assembly building, the VAB. You've seen pictures, everybody's seen pictures of the giant building at Kennedy. That's where all those parts are then assembled, stacked, or assembled into the total SLS rocket. There you go, there's the VAB. I've been in there. That is an impressive building. I've been there many times. That building is so big, it actually has its own environment inside the building. It can actually form dew and rain a little bit inside the building. It's really impressive.
Wow. You're right. That is very impressive. How many hours and staff will go into planning the Artemis mission?
That's a great question. I do not know how many hours. I would tell you it is a large team of people from across the country, because it's a very complicated thing. Mission planning is enormously complex. It involves, of course, all the performance of the vehicle. It involves the crew. It starts with objectives for the mission. What's the mission supposed to accomplish? And then how you incorporate all the planning for the crew and the vehicle performance, the launch trajectories, and all the contingency scenarios. Contingency scenarios are planning that are put in place for the event that something goes wrong, right? So those contingencies are there, very, very well thought through and planned to be able to react to whatever might occur during the mission. So it's a really complex operation involving people not just from Marshall Space Flight Center, where SLS is managed, but certainly from Johnson Space Center, where Orion is managed, and that's traditionally where back in Shuttle, the mission operations people were at Johnson, so they're certainly involved, and as well as a lot of people at Kennedy as well. So it's a big team.
Really does sound big.
Okay, Samantha, why don't we go one more question, then I'll kind of finish it up with Johnny.
All right. If you could offer your 14-year-old self advice, what would it be?
14-year-old self. That's a hard question. Because it starts with where you're at, right? So I'm actually at a great place. I love what I get to do. From a career perspective, it's been amazing. I would certainly go and say, work harder in school, be more determined and focused toward my academic career. But I think the big thing, it ties into something I said earlier, is to dream bigger. When I was 14, my vision, my dreams, my hopes for what my life would be as an adult was much smaller than it should have been. As I said, I never dreamed that I'd get to work for NASA. Certainly not to be a part of the Space Shuttle program, help build the International Space Station, and put crew in orbit all those times, and now be a part of the leadership team for SLS to take the nation back, the world back to the surface of the moon. I never dreamed I would get to do such a thing. So if I was going to go back, I would say, hey, think big for what your dreams really are, and realize that you're only limited by how hard you're willing to work.
I think that's a great answer. I oftentimes recommend myself a book that actually is a pretty quick read, but it's a wonderful book called The Magic of Thinking Big.
Oh, that's right.
Yeah, and it's really what you're emphasizing, because sometimes we don't fully understand when we're young what we really can do if we apply ourselves. And I will tell you that this is the best summary I've seen of the Artemis program, and makes it just a little more exciting even for us old people. How's that?
Thank you very much.
Yeah, and I know that you know, Sam, you know, at age 14, these are the kinds of things that make a phenomenal impression. You know, as we kind of wrap this up, okay, this is a little bit free form for you. I think you've expressed extremely well. You're growing up, you're dreaming, and like kind of a, wow, I'm here now, and I perhaps didn't expect to be there. Well, no, no, I think of going off of a catapult of an aircraft carrier, and I go, how the heck did I get here? And you know, you're exceptionally accomplished, and you get to work with wonderful people. So if you're going to pass on that message, that, you know, the words of wisdom, you know, that are special to you, because, you know, as we all get a little bit older, you know, we've got 2 or 3 things we like to pass on to those that are going to, they're going to join us. And in some cases, they're going to take us to, you know, the Star Trek, you know, and of course we have these public-private partnerships. So we have a tremendous amount of interest in your world.
So we've talked about dreaming. We've talked about working hard. You know, we all bring something to the table, right? Everybody does. And so don't be afraid to talk. Don't be afraid to ask questions. Don't be afraid to go ask for help, right? So one of the reasons I'm where I am today is I got helped along the way by some brilliant people and just wonderful people. And certainly within the NASA community, everybody that I've ever worked with at NASA is eager and willing to help. Work hard, dream big. You know, take advantage of the technology that's available to you now. It's so much different than it was when I was 14 years old. Clearly, there's so much more out there that's available to you. Utilize it in a way that's productive. I'm something of a social, you know, I tend to be a little bit more of a social media geek than I should, but I try to take those tools that are available to you and use them in a productive way, something that you get something tangible back from. I kind of just do this. I just flip, right? There's nothing tangible. There's nothing that I'm really getting from that. But that technology that's available to you, to the young people today, is so amazing. It opens up a whole new world of learning that wasn't available when I was a kid. So take advantage of that, but focus it toward what those big dreams are. But it's great. You know, it's NASA's a wonderful place to work. As I've said, I wouldn't change a thing throughout my 30-year career. It's been an absolute dream come true for me. And it's available, it's out there, as I pointed out earlier. It's available to anybody that wants to reach out and grab it. The aerospace business as a whole right now is in a really good position with all the commercial ventures that are taking place. So there are jobs, you know, back when I was a kid, it was NASA or nothing, right? But now you've got all the different commercial partners that are out there, and the supporting staff or supporting team of various contractors around the country. So jobs are all over the place out there. And the aerospace business that can allow you to be part of taking people back to the moon, and potentially, Samantha, in your lifetime, maybe trips to Mars.
Well, and I'm going to say something. You've kind of, and this could be maybe the new credo for NASA, but it's kind of NASA is fun. And, you know, sometimes we don't look at NASA as being fun, okay, because we don't understand it at the level that you do. You've been there, you know, for 30 years. And, you know, that fun factor counts with us. As you commented earlier, you know, if you really love what you're doing, you'll never work a day in your life. And
Absolutely.
that is absolutely so true. So, okay, you get to close out. You get to tell us anything you want. And we'll end it with you.
Well, number one, thank you guys. This has been a lot of fun. I hope I hope I was able to convey some of the great things that are going on within the Artemis program and the SLS launch vehicle. And on a broader sense, NASA is fun, right? It's large, it's diverse. There are a lot of things that you can get involved in. You don't have to build rocket engines to work for NASA. You can do a lot of different things. But it is a great place to work. And I encourage anybody out there that has an interest in the space program to follow us on social media and help us as we look forward to Artemis I and then boots on the moon in 24 via Artemis III. It's going to be historic. It's going to be fantastic. And thank you guys very, very much for your time today.
Well, we're all going to watch Johnny Heflin and NASA.
No, I'm just, I have the absolute privilege of leveraging a lot of great people that have come before me and standing on their shoulders, as well as standing shoulder to shoulder with some of the greatest people on the planet as we do this. It's not me, it's a large, fantastic team that are able to accomplish great things working together.
Well, thanks for being a great member of that great team and taking us into the future, which I really believe it's very, very exciting. So we're going to thank you, and we're going to close out. And please come visit the San Diego Air and Space Museum.
I will look you up next time when travel gets back to normal. I will look you up. I'll pay a visit. I've never been. Look forward to it.
Well, we'd love to see you here.
Thank you very much. You guys have a wonderful day.